Here's an interesting problem from the International Mathematical Olympiad 2021 held in Russia. This is problem 1, so it's the easiest problem on the hardest test. Let's dive in. Let n greater than or equal to 100 be an integer. Ivan writes the numbers n plus 1, ... up to 2n, each on different cards. He then shuffles these n plus 1 cards and divides them into 2 piles. Prove that at least one of the piles contains 2 cards such that the sum of their numbers is a perfect square. Let's ignore the rule that n must be at least 100 and just explore for a moment. Here is a pile of 8 cards, so let's deal them like so. Now our top and bottom rows are our 2 piles, are all perfect squares in different piles. 1 plus 15 equals 16, good, they're in different piles. 10 plus 6 equals 16, also fine. 19 plus 17, 36, no issues here. And 81 plus 19 is 100, perfect square, different piles. But look here. 1 plus 8 equals 9, a perfect square, and they are in the same pile. This doesn't satisfy the condition. So here is our claim. No matter how you sort these cards, you will always find at least one pair in the same pile whose sum is a perfect square. To illustrate this, we introduce the concept of neighbours. 2 numbers are neighbours if their sum is a perfect square. So on the TV show of the same name, Charlene lived at number 32 and Scott lived at number 26. Now 32 plus 26 is not a perfect square, so by our definition they were not neighbours. This diagram shows the neighbour relationships in the cards we saw before. The lines connect the neighbours, and I have also added in the extra number 25 as an example of a number that has no neighbour in this set. Our task is to see if the neighbours can all be separated. We can represent the piles as 2 colours, green and red. So let's put 19 in the green pile, then its neighbours must go in the red pile, and their neighbours in turn go in green, and then lastly the remaining neighbours go in the red pile, but you can see they are also neighbours, so they will be stuck together and there is a clash. And it's easy to see that if there is a loop with an odd number of nodes, a perfect square must occur in one pile, and otherwise it's possible to separate them. So our aim is to prove the statement from problem 1 by showing there will always be some such closed loop, remembering that we are only using numbers from n greater than or equal to 100 up to 2n, which is a tricky restriction. So let's search for these numbers. We will never find 7 numbers like this. For example, there are only 5 perfect squares we can make using numbers from n equals 100 up to 2n equals 200. So let's keep it simple. Let's look for 3 numbers that are all neighbours. Now you can never find 3 neighbours that produce 2 even perfect squares and 1 odd perfect square. So you can't get 16 squared equals 256, 17 squared equals 289, and 18 squared equals 324. The proof is a homework question for you. So let's try 17 squared equals 289, 18 squared equals 324, and 19 squared equals 381. We want 3 numbers where the sums of the numbers equal these perfect squares. Here I've set up a diagram for 3 cards to see if it is possible to get a loop of 3 neighbours. It's easy enough to get 2 perfect squares, take a number like 130 and find out what we have to add to get 289 on top and 324 down the side. The problem is getting the third number to equal 361 instead of 353. But look what happens when we change the 130 up or down by 1. If it goes up by 1, the other two numbers both go down by 1, and their sum goes down by 2. Now we want to go the other way. So each time we take that central number down, the other two go up by 1, and their sum goes up by 2. Since 353 is an odd number, if it increments by 2 each time, it will eventually hit 361. And then you can check that the numbers we have got are in range. So we have shown that for n equals 100, we can find 3 neighbours from n equals 100 up to 2n equals 200, as we had hoped. We can guess that this should be possible for larger values of n, because as n gets bigger, the total range of numbers grows. And I think that's enough messing about, so let's just get to the solution. We need 3 numbers, a, b and c, which are all neighbours. That means their sums are all perfect squares. The simplest is when the sums are 3 consecutive perfect squares. So let's write this in mathematical language. As you see below, the x squared, x plus 1 squared and x plus 2 squared consecutive perfect squares. You can confirm that for x equals 17, we have the example from before with the consecutive squares 17 squared, 18 squared, and 19 squared. Now we can assume the numbers a, b, and c are quadratics, just like their sums. If that doesn't work, we can try something else. Note here, below I have used the letters a, b, and c for the numbers, and then each of these uses a, b, and c for its coefficients. Sorry if this looks muddled. We define a, b, and c as quadratics with unknown coefficients, as you see here. We are going to solve for these coefficients by setting a plus b equals x squared, a plus c equals x plus 1 squared, and b plus c equals x plus 2 squared. We will put the quadratics for a, b, and c into the set of equations at the bottom, and then we will solve to find the coefficients. At that point, the proof will be about half finished. Okay, in this slide we have the basic equations at the top, and if you look below, you'll see that these scary long equations are just the equations from the top with the full quadratic expressions for a, b, and c substituted in. This will be clear if you check the previous slide. It looks heavy, but this is in fact just rewriting everything in mathematical language. It only says that a, b, and c are quadratics and that we have to find a large bunch of unknowns. Now we just ask, how many equations, how many unknowns? You should find there are 3 sets of 3 equations, each with 3 unknowns. And I've set this up here fully. These are the 3 sets that we have to solve. That's on the right. As long as each set is linearly independent and each set has as many equations as unknowns, we can solve algebraically, which will solve for real numbers. Then we must check that our solutions fit the actual problem, such as, for example, they have to be integers. We will check that after. And here are the solutions for those equations. You can simply check that by putting it into any online equation solver or graphical calculator. The coefficients are on the left, a1, a2, a3, etc. And the equations are on the right, where I have, of course, just put those coefficients into the equations. Now we must check, are they integers? Will there always be some number x so that a, b, and c are in range, remembering the range is from n greater than or equal to 100 to 2n. Are they integers? Check this yourself. pause the video if you need. They are integers when x is an odd integer. Initially they are in range, and of course x equals 17. Remember how we found this earlier. Do they stay in range? That depends on what happens when n becomes larger than a plus b. So checking the range of a, b and c, let's start with an example. When n equals 126, our original solution still works. A equals 126, b equals 163, c equals 198. But when n equals 127, a goes out of scope, so to speak. So we need a new a, b and c, all between 127 and 254. Remember, we will never be able to solve for a, b and c if only one of the perfect squares is odd. So x equals 18 will not work. Try it yourself. We need to use x equals 19. We put that into our equations and we get a equals 160, b equals 201, and c equals 240. These are between 127 and 254, so we are still in range. Does this always work? Let's prove. When a goes out of scope, n equals a plus 1, therefore n equals a half x squared, take x, take a half. Look at the equation for a and realize that I have just added 1 to that equation. And given that, we can say therefore 2n equals x squared take 2x take 1. Simply twice the equation for n. Then we substitute x becomes x plus 2 into the quadratic expressions for a, b and c. Then you prove that n greater than or equal to 100 gives us c, card c, less than or equal to 2n. Hint, just equate the quadratics, or else just ask ChatGPT. By equating the quadratics, you can move all of the terms over to one side and use the quadratic formula. That should prove 100% that it will always be in range for n greater than or equal to 100. Now your homework, look back at solving 3, the third slide in the solving sequence, and use the new equations phi instead of the equations there to find the cards a, b and c. Are the resulting equations different? If so, why? Remember before I just said a plus b equals x squared, then x plus 1 squared, then x plus 2 squared. Here we're trying 3 consecutive perfect squares, but we're lining them up differently as x take 1 squared, x plus 1 squared. It should give us the same proof, but it may not give us exactly the same equations. Just a slightly different way up the mountain. See if you can follow it through. And your second homework problem, the one I promised you. Take any set of numbers. Look at the pairwise sums, the sum of each pair of numbers. For example, the numbers 11, 10, 8 and 6 produce the sums 21, 19, 17, 18, 16 and 14. Here there is an odd number, that's 3, of odd numbers, 21, 19 and 17. Under what circumstances is it possible to have an odd number of odd numbers? Note that the IMO problem is about perfect squares, but the point here is that the logic applies to all integers. It doesn't matter whether we are talking perfect squares or all integers. And that's the video. Let me know what you think. Let me know if it was too hard, too easy, or just right. Thank you.